Hi everyone, my name is Sonia Kim. I'm from Facebook, and today I'm going to be presenting our paper, Code Prediction by Feeding Trees to Transformers, joint work with Zhimin Zhao, Yushi Tian, and Satish Chandra. So I'm a software engineer, and in the engineering world, there's this higher level everyone aims to reach called 10x engineer, which means that you're able to write and produce the same amount of code as 10 engineers combined. Basically, you're a coding genius. Now, some people reach the status by studying a lot of coding textbooks, doing a lot of coding practices, or just having a lot of experience under their belt. But today, I'm here to present this magic tool that will help anyone get there by having your IDE automatically write the correct code for you. And that tool is called Code Autocomplete. And this is exactly why in recent years, Code Autocomplete has become a hot topic, especially as a key component in IDEs as it boosts developer productivity. Not only does it save the effort of typing the next tokens, but it can also serve as a code discovery mechanism by helping find API names you might not have been familiar with. So how do we create such an autocomplete tool that is also accurate? Let's take a step back and see what's been done so far. In the very beginning, we have type-based autocomplete, and these are tools such as Eclipse and Jedi, where naive ranking is applied. Statically type-checked tokens are ranked alphabetically or with the simple count-based statistics. Now, this can work well if the list of candidates isn't too long, but if it is long, we need a smarter way to re-rank the candidate list more effectively. With the emergence of neural networks and NLP, people have applied them for code prediction as well. In literature, there's ample related work using RNNs and their variants, such as LSTMs, attention, and copy mechanism. So then, is autocomplete a solved problem? Let's take an example. Here we have a Python code snippet, and the goal for autocomplete models is to try to correctly predict argv. The three state-of-the-art models we have compared our work against in the paper correctly predicted it. However, let's take a different example in this code snippet, such as predicting socket. Unfortunately, the same three models were not able to predict them very well. Fortunately, with our three models that we have come up with in our paper, they're able to predict them much better. In fact, two of them predicted socket as the first rank. And although it is not shown in the slide, this is actually the case for the rest of the tokens shown in this code snippet, that our models were able to predict it much better than the previous state-of-the-art models. So, what's different about our models? Unless you've been living under a rock, I'm sure you guys have heard of these things called transformers, right? There are these two robots that can transform into cars and back into robots and fight each other. I think they also made a movie out of this or something. Well, in the machine learning world, turns out they mean a slightly different thing, but they're still very cool. They're the newest state-of-the-art language models in NLP designed for sequential language modeling. With the help of self-attention blocks, transformers are able to make connections between any two tokens at a sequence at once, which makes it a pretty powerful tool. So we thought, why not apply it to code? The natural next question is, how do we feed code into transformers? Well, there's two ways to do so. Tokenize source code as a linear sequence, or use an abstract syntax tree, or AST, of code. One advantage of using the AST is that we're able to convey some syntactic information to the model, but does this help perform the model better? This is the goal of our paper. We discuss different ways to convey tree structure information into transformers and observe whether it outperforms the tokenized representation. In the next few slides, I'm going to give a brief overview of our models and how it compares to the baseline models. For more information on the model that we have compared our work against, please check out our paper. So here we have the evaluation results for the 4 previous work that we have compared our work against. We use the Py150 dataset for evaluation, which consists of 100K Python files from GitHub for training and 50K files for evaluation. And the numbers reported here is the MRR. One thing to note here is that the latter three models incorporate some tree structure, which may explain the jump in MRR from sequence RNN. So now we're going to explain our models, and our first model is called TravTrans, which applies a transformer over the source code token sequences. In our case, we use GPT-2 specifically. And you can see that this model already outperforms seq-RNN significantly, but not the other models that incorporate tree structure. So we thought, let's incorporate some tree structure. So our next model is called TravTrans, which applies a transformer over the ASD leaf token sequences, augmented with the root paths. And root paths are paths traversing from leaf nodes to the root. Thus, this is able to incorporate some tree structure since every leaf node is augmented with its parent and ancestor node information. And our results already show that this model is able to outperform all of the existing models quite significantly. The next model that we have come up with is TravTrans, which is another method to incorporating tree structure. This model applies a transformer over the ASD nodes serialized using a pre-ordered reversal. And our results show that this model outperforms our previous model, TravTrans, by 3%, and all of the other models quite significantly as well. So we thought, can we do even better? So here we experimented with an extension of our TravTrans model called TravTrans Plus that incorporates even more tree structure. One consequence of linearizing the ASD and pre-order traversal is that we lose some information. We no longer know whether two consecutive nodes have a parent-child relationship or a sibling-sibling relationship. So what we did was enhance the model by adding tree relations between two nodes in the self-contention block. The figure on the left shows an example of a tree relation between two leaf nodes. To go from the node that's at the start of the arrow to the end, it has to traverse up two nodes and down two nodes, hence resulting in the tree relation of up to and down to. In terms of the evaluation results, this model is actually able to outperform the best out of all of the models. And to summarize our work, our paper answers these high-level questions. Research question 1, given a source token sequence, does a transformer work better than an RNN as in previous work? Answer to that was yes. Research question 2, do the transformer models on tree outperform previous work on ASD-based prediction? Answer to that was also yes. Research question 3, does adding syntactic structure help? Unsurprisingly, the answer to that was also yes. And we show this by our best model significantly outperforming all 3 or 4 state-of-the-art models from previous work by a large margin of 10%. Furthermore, in this paper, we use saliency maps to examine where the model focuses its attention when making a prediction, thus shedding some light into model interpretability. For more information and for further details, please check out our paper. And for those who are interested, the code is available on GitHub. And with that, we conclude this talk, and thank you for the time.
All right. Hello, everybody. This is the Q&A for the paper Code Prediction by Feeding Trees to Transformers. And Sonia Kim will be the one answering the questions. It appears that we have the first question on the Q&A already, which is from Mikhail Yevtikiev. Do you plan to ship your model as an IDE plugin?
Hi, that's a very good question. And at Facebook, we actually have plugged this into the IDE plugin. So it's live for the developers at Facebook that use Hack and Python. And this is also a pretty good segue into kind of introducing the next paper, which I'm also part of, where we discuss the differences in doing offline evaluation for code prediction on the valuation data set versus the differences when you actually do plug it into an IDE plugin and see how the evaluation and how kind of like the patterns do change. So watch out for the next talk.
All right. Folks, other questions? Okay, I'm going to ask one while allowing you to type. So while we were waiting, okay, never mind. The question is from Ariaz Iqbali. Have you investigated other languages?
So far, we've only practiced our findings on Hack and Python just because those are the two largest languages that are used at Facebook. But in the future work, that's definitely something that we're trying to work on.
Okay, so I'm going to try to ask my questions. While we were talking in the backstage, one of the questions that came up was, given that the code completion may not be perfect, sometimes there are reasons to ask the developer to pick from the drop-down menu. And my question is whether you have measured how frequently this happens.
How frequent people...
How frequently they need to pick from a menu. Mm-hmm. And when they pick, I guess, how frequently is it that the top choice is not the right choice?
Yeah, so for privacy issues, I don't think I can release exactly like what the percentage is, but our autocomplete is always going to be a drop-down menu. So you are going to have to do a one click into, choosing down and then choosing maybe like return or tab. Our precision, however, is good enough that most people do click it within the first 3 drop-down menus.
All right, thank you. Question on the chat from Fahad Al-Dibian. Thank you for the talk. How was the data set labeled?
The data set we use for Pi 150 has been released by ETH, Zurich, and they already labeled with the AST and divided up into the training and evaluation.
All right. I think everybody is waiting for your next talk because, of course, one of the big questions in everybody's mind is what is the usage and how effective and stuff like that. And I think we're all waiting for you to tell us about the second paper before people discuss this.
Yeah, I think it's a great topic, especially just because it doesn't matter, how much research you do. Eventually, you do want to make it a little bit practical, and one way to do that is to plug it into an IDE. And we found quite stark differences when you kind of just take out of the box learning that you've done on offline and plug it into online evaluation. So it is very interesting.
Looking forward to that talk. Folks, other questions? Okay. Maybe as a precursor to the next talk, you can tell us something about that next paper?
Sure.
Hold on. So we have the question from Gabriel Bavota. Great work. You're predicting the next token, and I expect different types of tokens to be more or less difficult to predict. For example, language keywords are likely easier to predict, while identifiers are more difficult. Did you analyze such differences?
Yeah, I believe in the paper, maybe in the appendix, we do have a table that lists out different types. So things like attribute access, parameters, string literal numbers, and there are differences. So like numbers, you can imagine that it's a little bit easier to predict because a lot of them tend to be like 0 to 10, while like string literals are pretty hard to predict just because it can be anything. So if you check out our paper, we do have a table that lists out the differences.
All right, thank you. And now we have a question from Mikhail Yevtikhiev. A code in writing for which you suggest token may not be syntactically correct. So it seems that AST may fail to build. How do you get around this issue?
Yeah, that's also a great question. So in production, we have been using just the sequenced, tokenized code. So it doesn't use ASDs, and that's also for another issue when you move things from research to production is that latency is a very big issue for code autocomplete specifically, because you have to get the responses out in a certain time period. And it's usually less than 100 milliseconds, because you can imagine that if it takes like 5 seconds, it doesn't matter how precise and accurate your results are, people are going to use that 5 seconds to type whatever they wanted anyways. So for that reason, we are using just a sequence token. And so it might be the case that it might, like, statically it might not work out, but we do have another check that checks it to make sure it's statically typed.
So I'm actually not sure that I followed. So you're fixing the static typing as you are recommending?
Yeah, so in production, what we do is we get a list of statically typed candidates, and then we are re-ranking it using that list.
Okay. Folks, other questions? All right, I'm going to have one more. How big are snippets of code that you can meaningfully recommend?
So far in this paper, we have done just next token prediction, so it's just one. It's definitely in the future work that we want to expand it out to multiple token predictions, whether it's like 3 tokens, end of the line, maybe even multi-line. But in this work and in the next paper, it is focused on just one.
Okay. All right, and we have the thank you for the talk and for the answers.
Thank you for the questions.
And we have some clapping.
Yay.
So one more question then from me. The first question that you started answering was about shipping the model as an IDE plugin. But I think the question that a lot of us are wondering is if others want to experiment with your solutions, what is available and what we need to wait for.
Yeah, that's a great question. So the data set that we played around with Pi 150 is available online, and the code that we use for the model is available on GitHub as well. And the GitHub link should be in the paper somewhere. And also, I think I listed in the presentation.
All right, sounds good. So we have about a minute before this event ends. Those people who would like to continue discussing with Sonia and Satish are welcome to click once this appears, the button that says go to the discussion area. And otherwise, those of you participating will be automatically put into viewing a video of the second paper that keeps on being advertised. And then we'll be back for the Q&A with Satish and Sonia.
Marsha, quick question. How do I join the discussion? Or am I going to be...
You will see a big blue button that says go to the discussion. It will appear in 17, 16, 15, 14 seconds, and it is very hard to miss.
Got it.
And those of you who don't want to do it don't need to do anything. You'll just be automatically moved to the next talk. Thank you all for your questions.
Hi.